Fluid mechanics is a fundamental branch of physics that studies the behavior of fluids, both liquids and gases, under various conditions. Today, we'll explore one of its most important principles, Bernoulli's equation. Fluid mechanics encompasses the study of both liquids, which have definite volume but take the shape of their container, and gases, which expand to fill any available space. Fluid dynamics focuses specifically on fluids in motion. We visualize this motion using streamlines, imaginary lines that show the path fluid particles follow as they flow. Bernoulli's principle states a fundamental relationship in fluid flow. When the speed of a fluid increases, its pressure decreases. This inverse relationship is key to understanding many fluid phenomena. Bernoulli's equation mathematically expresses this principle. The equation states that the sum of pressure, kinetic energy per unit volume, and potential energy per unit volume remains constant along a streamline. Let's examine each variable in the equation. P represents pressure, ρ is the fluid density, v is the fluid velocity, g is gravitational acceleration, and h is the height above a reference level. Bernoulli's equation is fundamentally a statement of energy conservation for flowing fluids. It shows that the total mechanical energy, consisting of pressure energy, kinetic energy, and potential energy, remains constant along a streamline. For Bernoulli's equation to be valid, we must make several important assumptions. The fluid must be incompressible with constant density, inviscid with no internal friction, the flow must be steady and not changing with time, and we apply the equation along a single streamline. These assumptions allow us to apply Bernoulli's equation to many practical situations, making it one of the most useful tools in fluid mechanics for analyzing everything from airplane wings to water flow in pipes. Aircraft wings demonstrate one of the most important applications of Bernoulli's equation. The curved shape of a wing creates different airspeeds above and below the wing surface. The faster airflow over the curved upper surface creates lower pressure, while slower airflow below creates higher pressure. This pressure difference generates lift force that keeps the aircraft airborne. A Venturi meter uses Bernoulli's equation to measure fluid flow rate. It consists of a pipe with a narrow constriction where the fluid must speed up to pass through. As fluid enters the narrow section, it speeds up according to the continuity equation. By Bernoulli's principle, this increased velocity creates lower pressure in the constriction. The pressure difference between the wide and narrow sections is measured and used to calculate the flow rate. This makes the Venturi meter a reliable flow measurement device. In a carburetor, Bernoulli's principle controls the fuel-air mixture for internal combustion engines. Air flows through a narrow passage called the Venturi, creating low pressure that draws fuel from the fuel bowl. Bernoulli's principle appears in many other applications. Sailboats use pressure differences on their sails to harness wind power. Atomizers and spray bottles create fine mists by using high-speed air to reduce pressure and draw up liquid. It's crucial to understand when Bernoulli's equation applies. The fluid must be incompressible, inviscid, and flowing steadily. The equation assumes no energy losses due to friction or turbulence. Despite these limitations, Bernoulli's equation remains invaluable for understanding fluid behavior in engineering applications, from aircraft design to industrial flow measurement systems.